Hello everyone, I'm Dr. Hannah Lonsdale, Clinical Fellow in Pediatric Anesthesia at Johns Hopkins Hospital. Thank you to the IARS for the opportunity to present today and to all of you who have chosen this virtual session. I have no disclosures. It feels like machine learning is everywhere right now. We can't drive anywhere without using our GPS. We have little devices in our home that answer our questions. And even in our wallets, our credit card companies are using machine learning to protect us from fraud. And when many people hear artificial intelligence or machine learning, they think of humanoid robots like this one. But in reality, machine learning refers to computer programs that may also be called algorithms that give computers the ability to perform human-like actions, such as problem solving, object and word recognition, inference of world states, and decision-making by generating complex mathematical functions. And these algorithms are used to generate predictions about future events by a group of wonderful people known as data scientists who manipulate computer code in languages like Python or R. So in reality, this is what machine learning looks like. And it sits within the broader scope of artificial intelligence, the theory and development of computer systems that are able to perform tasks that normally require human intelligence. So did anyone start today with the question, well, why should I bother with machine learning when we have all these established biostatistics techniques that give us great results? And if we were in a live conference room in Hawaii right now, I'd ask for a show of hands, but I imagine there'd be quite a few if we were honest. Well, here's the thing. Machine learning is statistics. Many data scientists come from a stats background. And the only difference with the statistics we call machine learning is the amount of human guidance in the data analysis process. So for data sets involving thousands of patients with hundreds of input fields, where complex nonlinear relationships may exist between multiple variables, machine learning is likely to be more efficient and may offer the potential for deeper insight. And the other and more exciting reason for using machine learning is for its role in deeply personalizing treatment, with the ability to make tailored recommendations for an individual patient, rather than our current treatment guidelines, which frequently generalize a uniform treatment for every patient with a specific risk or condition. Let's dive into the data. And here's a term that gets thrown around a lot, but what does it actually mean? And it turns out that this originally came from the marketing industry, and that there is no strict definition of the size of a data set for it to qualify under this umbrella. I'm not a huge fan of the term, but it's the easiest phrase we have to describe data of sufficient volume, variety, and coming in such velocity to be difficult for humans or even most standard statistical techniques to process. And therefore, this is where machine learning really comes into play. And these data sets also need to be labeled. A label lists the outcome of interest for each individual record in the data set. So that might be whether a retinal image is from a healthy patient or one with glaucoma, or whether the data set belongs to a patient who had perioperative AKI or not. But where are these enormous labeled data sets sitting around in medicine? Okay, so we don't really have medical records like this anymore. But every day around the world, millions of pieces of data are entered into electronic health and medical records by people like you and I in the course of our routine clinical patient care. Without machine learning to help us dig into that vast repository of knowledge, is the EHR really any better than a digital version of the same storage system that we've been using for over 200 years? Now, our large data sets might come from the EHR of one organization or of many. They could come from a registry or as a secondary use of data collected for another study. Machine learning is very much a team sport. Most of us here today are clinicians, and as such, we're subject matter experts in our fields. Data scientists who develop the machine learning algorithms need expert clinical collaboration to select the most appropriate fields and to examine the feasibility of the values that the model produces. So just as most of us in the audience today can't program computers using Python coding, data scientists don't know what information from a data set would be available and useful to the clinical team during preoperative assessment. And there's actually a whole heap of stakeholders involved in taking a machine learning model successfully from data set to clinical workflow. And this group has been termed the AI care team. And it may include data scientists and engineers, expert clinicians like you and I, IT support, the end user providers, ethicists, and a project manager to make it all happen. And ideally for machine learning, we need data that is of high quality, clinically relevant, with few missing values, and is closely related to the population we wish to study. How often do you think that happens just like that? And therefore, we probably need to do some work before we can let the computer start to learn. And this is known as pre-processing or data cleaning. In reality, this work usually takes the data science team much longer than developing the algorithms themselves. Anyone who has done any data collection can likely empathize. And my appeal to you as a research and clinical community is to think about how we currently collect data through our electronic records and to optimize this so it's not just that storage bank of files, but is a powerful living system that can be tapped for new discovery and insights to benefit our patients. And data pre-processing involves several steps, such as removing outliers, like a respiratory rate of 200, likely a typo. Imputing missing data. Machine learning doesn't function well when values are missing. And there are techniques that range from simple, removing that record or variable from the analysis, to complex, statistically computing multiple plausible options and allowing the model to work on all of them. We need to select the appropriate features or inputs. Machine learning can accommodate hundreds or thousands of variables, but allowing models to use data fields that are irrelevant or highly unlikely to add value is at best inefficient and at worst can actually lower the model's performance. We also need to be sure to use only features that would be available at the time the model is clinically useful. It's no use taking the amount of intraoperative fluid given from your retrospective data set and using that as a feature in a model that would be used to give a preoperative prediction of a need for vasopressors. That fluid volume information would not be available preoperatively for a prospective patient. And that is why these processes must be guided by subject matter expert physicians working closely with data scientists. Once we have our beautifully clean pre-processed data set and have selected the appropriate fields, we divide that data into a training and testing set on a ratio, for example, of 70-30. The algorithm begins by examining the training data set and formulates a statistical rule. It then selects out the correct and incorrect predictions, reviews the incorrect answers, and alters the statistical rule to take account of those errors. Unlike us, the algorithm starts from a point of zero knowledge, so it takes many, many, many iterations to produce a statistical rule that accommodates those complex nonlinear interactions. But once that algorithm reaches a point with little improvement after new iterations, the testing set is used to assess its performance. Remember that the computer starts from a place of zero knowledge, so the more data we have, ideally thousands of labeled data samples, is needed. And that's why machine learning is only now coming into use in medicine. It's common for data scientists to use several types of machine learning algorithms on a data set and then select the one which performs best, as each type of algorithm has its own strengths and weaknesses. You may notice a third division here. There may be an extra set of the training data held out, called a validation set. And this is used to tune the machine learning model's hyperparameters. They're the controls on the model's learning process. And these may include the learning rate and the batch size, or the number of records or samples that the program will analyze each time before checking for errors and altering its statistical rule. Here's our patient cohort. We would like our machine learning algorithm to draw a line that perfectly divides which patients are going to be blue from those that are going to be red. And it might look something like this after the machine learning model has finished all of its training iterations. It's a complex statistical formula to divide the data. But the sharp-eyed in the audience will notice that there are some dots on the wrong side of this line. So what would happen if we went a little further? So the only way to divide all the patients into the correct group looks like this green line. It's really messy. And it's also a big problem. Any idea why? So when a model is too closely fitted to nuances in the training data set rather than to the population of interest broadly, its performance is reduced when used prospectively on new data. And this is known as overfitting, and it's something that we work very hard to avoid. And to check that we haven't overfitted our model, we need new data from a similar group of patients that the model has not yet seen to check our model's performance. And that is why we hold out that testing set. There is no one measure that can tell you how good or bad a machine learning model performs, but I'll cover a couple of the most important techniques here. The most commonly reported measure is area under the receiver operating characteristic curve, or AUROC. And here we have the ROC from this study, with a little reminder that there are multiple names for things and stats. A perfect model would have an AUROC of 1 with a straight line across the top of the chart. A model that performs no better than random chance would have an AUROC of 0.5, shown on this curve as a dashed red line. The other colored curves here are the performance of several different types of machine learning model, which in this study performs all very similarly. For any given model, the threshold at which it makes the call of positive or negative for the predictive outcome can be adjusted. And you can think about this like setting a hemoglobin level that would trigger perioperative transfusion. The higher we set the threshold hemoglobin level to give a transfusion, the more we prevent complications of low hemoglobin and anemia. But the more patients receive transfusions with their associated risks. We need to set that threshold at a level that prompts an action or intervention to encourage a change in practice that carries the most benefit for patients. If I wanted to minimize false positive predictions that might overwhelm providers with false alarms and alert fatigue, I might set a low threshold, accepting that I would miss some of the cases. But if the cost of missing cases was high, let's say for use of a life-saving treatment, I might accept more false positives as a trade-off for increasing my true positive rate. Here, I catch about 80% of cases, but 60% of my predictions are false positives. There are both statistical and clinical ways to decide how to set the threshold. And in anesthesia, many of the outcomes we wish to predict, such as perioperative morbidity, are relatively rare. This is an important challenge for machine learning and all predictive statistics. When prevalence is low, the ratio of positive and negative outcomes is very high. And we call this class imbalance. Therefore, we also need a measure of performance that takes account of prevalence. If the model indicates that our patient is predicted to have, for instance, perioperative morbidity, PPV, positive predictive value, tells us how likely that patient is to actually experience the outcome they have predicted. Many current machine learning papers in medicine don't report this number, even when they have huge AUROC results of 0.9 or more. Because when the outcome of interest is rare, the model has far fewer records to figure out patterns to make a correct prediction. When we think about the future clinical utility of machine learning, this illustrates the importance of selecting the correct problem to address, curating the largest possible complete data set to train our models, and assessing their generalizability to new data sets. And in machine learning, this assessment is known as validation. As we already touched upon, validation describes testing the model's performance on data sets and data combinations beyond that initial training set. And we've already encountered a type of internal validation, the held out testing set. Others you might see mentioned in studies include k-fold cross-validation and bootstrapping. And these are all types of split sample validation. But we want to go further to see if our model is generalizable beyond our starting data set. And this is called external validation. We might collect new data from the same source to run our model and test its performance. And this is called temporal validation. Or we might get data from similar patients with the same set of variables, but from a different hospital site, or even a different country. And this is geographic validation. Once we think that we have a validated model that will be really useful in the clinical workflow, that's really only the start of the work, as we will shortly learn from Parisa and Jonathan. No machine learning model is perfect, and they are all intended to be used as decision support and guidance, and not as a substitute for clinical acumen. We're not about to be out of a job anytime soon as a result of machine learning or artificial intelligence, but it could help us in the future to offer precise and individualized care to our patients. Thanks for listening today. I'm happy to chat further through email or social media, and I'm really looking forward to your questions during the discussion.
Hi everyone, thanks for attending this talk today. Today I will be talking about artificial intelligence and building more interpretable, explainable, and usable models. Here's the outline of my talk. First, I will have a very brief introduction to some of the concepts in this area. I will talk a little bit about the terminology, some of the basic concepts, as well as some of the more advanced and state-of-the-art techniques that we can use. And then I will talk a little bit also about limitation and future opportunities for improvement. In recent years, deep learning models have become common in many domains, including in healthcare, and they provide lots of advantages. For example, we no longer need to do manual feature engineering. They provide better performance, and they allow us to capitalize on large data sets and to learn from such data sets in data-driven manner. At the same time, they have a significant drawback, which could be important for healthcare tasks. And that drawback is that they are not interpretable or explainable in their very basic forms. And therefore, the model decisions and some of the important features for the decision-making process are not inherently provided by these models. Now, I want to talk a little bit about some of the terms that we will be using. Global interpretability versus local interpretability, that's an important concept that sometimes comes up. Global interpretability basically means how the model works globally by inspecting the structure, the architecture, and the parameters of the model itself, regardless of a specific data point. Local interpretability, on the other hand, examines the individual prediction for a specific data point for a model. And that's why we call it local. Then there's also the terminology for intrinsic versus post hoc explanation. The intrinsic explanation are the explanation that are provided to us through a model that has been modified in some way, that the architecture has been built in some way to provide explanation. On the other hand, the post hoc explanation are obtained from a model that was not built necessarily with interpretation or explanation in mind, and we are changing and modifying the output or the parameters of the model, post-processing them in some way to obtain the explanations. Now, you might be asking, what are the differences between explainability and interpretability? I have been using these two terms together, but of course there are some differences. And I think this diagram here can help us in terms of understanding the differences. So as we have said, deep learning models in their very basic forms are just black box models, as we can see here. Now, once we add some form of interpretability mechanism, which we will talk about that, then we can understand how input is mapped to the output by the model. In other words, we can understand the mechanics. We can use that for troubleshooting the model. And in many cases, that can be especially very helpful for model developers to see why they are getting a certain prediction. Now, we can go beyond that and we can have explainable models. And explainable models is a type of model that can also provide explanation on why a certain prediction was made. And it can answer questions such as how this prediction was made, why we are not getting a different type of prediction, what else could happen, what if I replace this input by another input. And so that's kind of similar to how we as humans, we prefer explanation. And of course, on top of that, we usually have some sort of interface that can provide this interpretation and explanation to humans, to physicians, and that can be also important. That's where the usability comes into play. And on top of all of this, we need to also evaluate those concepts. We need to evaluate explainability, usability, interpretability to see if those models that we have developed, those methods that we have implemented, are they really helpful or not? I think that we can all agree that there is a need for transparency and the inability to understand the model decision-making process. Sometimes it might lead to even catastrophic consequences, and it could also lead to a lack of trust, being unable to diagnose problems, and a host of other undetected issues. And this has been highlighted by many papers and publications in recent years, as you can see some of the examples here. So it is very important to have that transparency if that can be provided by some form of mechanism such as interpretability or explainability. In terms of the legal implication, recently also there have been a number of initiatives. For example, in General Data Protection Regulation from European Union, GDPR, there are some clauses that explicitly relate to this. For example, that the subjects, they have a right to obtain explanation of the decision reached after assessment and to challenge that decisions. And those can have implications for all of our models that we are developing. In terms of the methods that we can use, there are a number of simple methods that were developed in the early days, and those can include techniques such as simply visualizing the weights in a neural network, like this one here, or visualizing the filters, or visualizing the embeddings. And those were simple techniques. And then a number of other techniques were developed to kind of build on that and to improve those techniques, such as maximum activation, where an input I is maximizing the activation of a unit Z corresponding to a node in the network, and then based on that we can understand which one of the inputs maximally activate a node in the network, and that can be helpful for, again, diagnosing the model. There also have been a number of more recent techniques that we have seen in recent years, especially again for a case of deep neural networks, such as the class activation maps, saliency maps that can examine the saliency of individual features by superimposing the saliency on features, or masking the input and then providing that to the algorithm and looking at the corresponding output, and based on that finding out which one of the inputs are important for a certain task. And here you can see that, for example, in case of molecules that were provided to a neural network, which one of the bonds are important, which one of the atoms can be important here. And then there also, of course, has been the attention mechanism, which has been used a lot in many of the recent architecture. And it has been very helpful in language models. It has been very helpful in models that have been developed for analyzing time series data, for image data using vision transformers. And again, all of those are different types of techniques that we can use in order to make a model more interpretable. There also has been a technique called LIME that is model agnostic. So the previous techniques that I showed to you, most of those have been developed for neural networks. And although you can change them, some of them to some extent, to adapt them maybe to a different setting, but at the end of the day, most of them are just developed for neural networks. Now, LIME is model agnostic. You can apply that to any technique, and it can help us to understand a model by perturbing the input of data samples and then looking at how that perturbation changes the prediction. And it learns a sparse linear model around those data points, and that can provide a better explanation around those data points in a local way. And here you can see the original paper. So this is again a nice approach. Many people are using LIME, and it's simple enough to be implemented. In terms of existing work, there have been also a number of recent work in many different domains. For example, in pathology, in mammogram classification. We have done some work for analyzing time series data and highlighting the important time point in physiological signals that can relate to, for example, acuity state of a patient. As you can see here, we have done something similar using SHAP technique for highlighting which one of the features are important in terms of prediction of post-operative complications. Now, I talked about these concepts a lot, and we have seen how they can be useful. But ultimately, although giving explanation can increase understanding of trust in a system, sometimes those simple explanations can also hide some undesirable attributes of the system and might mislead the users into dangerous or sometimes unfounded conclusions that could ultimately be unethical and could be ultimately harmful for the patients. So it's important that we understand that those techniques also have their own shortcomings. Those are not perfect techniques, and we should not be just blindly embracing the explanation as, again, because sometimes they might not be perfect, and that could disguise racial or gender discrimination. And if you're just trusting them and we say, see, I have explainability of the model and it tells me that there is no gender discrimination, there is no racial discrimination, but there might be something going on, and it can provide what we can call as kind of fair washing, which is the phenomena where we are promoting the false perception that a machine learning model respects some ethical values, but of course underneath that there might be some imperfection that we cannot see. So my final thoughts are that as opposed to just simply focusing on interpretability and explainability as concepts, we should focus on the end users' goals and requirements and needs. And we should embrace a diagnostic vision, and we should be open to accepting that these methods themselves also might have their own shortcomings, and we should try to improve them at the same time that we are improving our underlying architectures and models. And that's what I have for this talk. Thanks again for listening, and let me know if you have any questions.
Hello there. This is Jonathan Warner here today to talk to you about putting models in motion, the good, bad, and the ugly of artificial intelligence clinical implementation. Now, I don't have any disclosures to make, but always looking to get things to disclose. If you have any good opportunities, please send them my way. Here is the goals and objectives as well as a roadmap. We're going to talk about an implementation framework, move on to then some practical examples, finally talk through some limitations of machine learning, as well as where we go from here. So I would suggest that you consider using this as you approach implementing machine learning models. First step, develop a model. We spent a fair amount of time discussing how that can be done. The second is to utilize an implementation framework, which we'll be talking through next. And finally, to establish governance, so you have a way to monitor your models over time, as well as maintain them as needed. This is a focus PDCA approach to model implementation. And so the F in focus is fine. First, establish what the main problem is before assuming that a predictive model will be the right way to solve it. O for organize. So you need to get all the right people together. Have folks with clinical knowledge, so know what treatments to recommend. Have an analytics support to understand how to manage various features of the model. Have technical expertise to understand how this model could actually be implemented, and most importantly, have good involvement from your bedside clinicians so you can have an understanding of how this will impact clinical workflow. The C is for clarify. So you need to understand the current processes that are involved in your solution and your problem. Understand if there are any current models that are in use or any mental models that people have when they think about the problem. And also consider what would be a successful outcome for your clinical problem. U is for understanding, so understand the factors that influence the problem, as well as understand the root cause. You can find yourself asking why a few times to get down to the root cause for any particular issue. And then finally, select the model that you're going to use. There are a variety of ways that you can measure model performance, as we've discussed, and it's important to review those in advance of model implementation. Next, you want to undergo some PDCA cycles. So plan a place to do a pilot of your model, and then turn the model on. Gather data from the pilot implementation, make sure it's going as you anticipate, and then act on that information and adjust the model to understand things that went well, as well as things that may not have gone as well as you had hoped before you consider a full-scale rollout. There are a number of operational considerations for implementation. Here are a few important points. We'll need to make a decision between creating a local model versus implementing someone else's model. Now, if you create a local model, you'll need a well-curated data set as well as technical expertise to do that. Whereas if you're implementing someone else's model, you need to figure out how to do the parameter mapping and then understand model performance at your institution prior to implementation. Maintenance is important because the data inputs may change over time, or your operational process may change. And in fact, some of the models, depending upon the inputs, implementing them may change the data that comes back in. And so this will require putting in place a way to monitor the models and maybe potentially retrain them on an annual basis in order to have them continue to perform well. And lastly, I recommend putting in place a governance structure so you've got some folks with dedicated effort and attention to overseeing the implementation as well as the maintenance of the models. We're going to move next to some practical examples. And so this is one that I would consider the good in the capacity management bucket. And so this is a model that we created a number of years ago for doing prediction of surgical case volume. So predicting the number of cases per day in the OR. As you can see from the graph, there's a lot of variability in how many cases we have per day. There are obviously downsides to over as well as understaffing. And so we wanted to see if we could predict OR volume with a good degree of accuracy. And we found that we were able to do that with an ensemble of linear regression models. And if you look at the graph, you'll see an OR day represented by a single colored line there and 2 weeks of scheduling data prior to the day of surgery. And you'll see that cases accrue for a given OR day on a linear-ish trajectory up until about 2 days before, when you have this inflection point and suddenly more cases start to accrue. And so you're able to model that linear behavior. And this is what we found to work pretty well. And we're able to get within 8 cases, 2 weeks out, and within 7 cases, 7 days out, 80% of the time. We operationalize this with an email, which we send out 5 days prior to the OR day, and we use this to adjust staffing. This is for our nursing, our case preparation center, surgical pathology, as well as anesthesia staffing, and allows us to detect things like a surgeon conference, which hadn't been declared in terms of adjusting the block schedule, but let us utilize our resources well. Here's another example from capacity management. I consider this the bad. And so we created a local model for post-acute care discharge needs, trying to predict if someone's going to a SNF, long-term acute care, or inpatient rehab. You can see the model inputs there. Those are things that are readily available in our electronic medical record within the first 24 hours after admission. And we created the model. We found that it worked very well. Excellent performance, AUC 0.875, great calibration, outstanding model performance is what we called it. We got through the workflow integration with a dedicated patient list and a column that our case managers and discharge planners could see. And then we started getting user feedback as part of a pilot of this work. And our users said, this thing appears to be broken. It was not what we were expecting, given the overall excellent performance. So we did a revalidation with a recent cohort to see if maybe the population had changed. It hadn't. AUC was about the same as the old as well as in the new. And then we looked at the cohort a little bit more carefully, realized with a 10% threshold for discharge, which we had picked as our trigger, that we had a positive predictive value of only 23%, which meant that the majority of the positive flags on these patients, in fact, were on patients who ended up going home. And so ultimately, we had to reset our staff expectations in terms of how well this would work and revise the workflow. We were able to reduce the noise by increasing this threshold to 50%, as well as targeting those with the stated plan of a discharge home. And now our district planners review this on a daily basis and continue to give us feedback on how to improve the model performance. Next example is what I would call the ugly, and this was Epic's estimated length of stay model. So this is a model that gives you an introvert prediction of the number of days left in someone's hospital encounter, and everything goes into this model. It's the whole kitchen sink. So flow sheets and labs, LBAs, beds, procedures, surgeries, risk scores, everything. And here we decided to turn this on silently and collect data for 3 months. We did that, and in terms of expectations, we were told this should be directionally correct, so useful for rank ordering and had better performance than other ways of doing this, such as geometric mean length of stay based on a DRG. But we found that we had inconsistent model output. We didn't have predictions where we expected them. It was only after a phone call with Epic that we understood that we were only getting estimates from the model within the first 24 to 96 hours after inpatient admission, and then the model just stops giving answers. And so we found this to be not usable from an operational perspective, and so didn't go any farther with its implementation. In the operating room environment, there are a number of artificial intelligence type tools that have been demonstrated to have really good performance. And so we've got closed loop controls around things like muscle relaxant dosing, keep your train of thought at a certain target, depth of anesthesia, maintaining this at a certain target, and optimizing stroke volume in terms of fluid administration. To give an example of what some of that validation work looks like, this is a really cool example where the authors phlebotomized a pig. So you bleed the pig, and you pit the anesthesiologist group against the learning intravenous resuscitator, which is a pump plus a model. And you can see the outcome in the graphs to the upper right. And so on the right-hand side, you've got the closed loop control, heart rate, and mean arterial blood pressure. And you'll notice that the lines are pretty straight, meaning not very much variability. Whereas on the left, the anesthesiologist in control, you see a lot of gray squiggles, which is to say that the anesthesiologist is having more swings in heart rate and mean arterial blood pressure. So ultimately had a better cardiac index with the AI approach, no difference in overall fluid administered, but lower variation throughout. You might say, if we put these things together, what is the impact on patient outcomes? And this is a neat study and an infographic summarizing it where they did that. So in this study, they took a group of patients, randomized them to either closed loop controls versus a human being. And the controls they used were BIS, end-tidal CO2, and fluid, and found that the AI used many more frequent changes compared to the human and was on target much more frequently. The outcome here was the Montreal Cognitive Assessment, where you had a statistically significant improvement, although maybe not clinically relevant, in the closed loop controls versus the human. Now, it's not just in the OR where we find this technology being potentially very useful. This study looked at ECGs and trained convolutional neural network to identify 21 different rhythm classes, and they looked at diagnostic accuracy. What they found is the model performed better than even physicians with 12 plus years of experience. So you have overall AUC of 0.983 and a lot of accuracy. So clearly, AI can be used to read ECGs from a rhythm perspective. There's also other information they can pull up that you wouldn't even think was there. This is a paper where the authors were able to get a machine learning algorithm to pull out age and sex from an ECG. And they did it with a high degree of accuracy. AUC of 0.97 for sex, age within 7 years. And you might say, well, that's neat, but not useful because you can generally tell how old in someone's sex by looking at the chart. But you can get other information that is potentially useful. And so in this example, the team was able to get low ejection fraction out of an ECG with a pretty good amount of accuracy, 85.7% overall. Not just ECGs you can use these for. There's been work done on echo interpretation. This team was able to use machine learning to identify viewpoints from echo images, as well as do cardiac segmentation, calculate volume, LV mass, and ejection fraction, as well as have some pretty high performance for diagnostic accuracy for a variety of cardiac conditions. I think that's cool. You should see this, and this is AI being used to provide real-time echo guidance in terms of how you are able to optimize your images. And so the AI provides specific feedback to the person holding the probe and is able to optimize the image, and then will automatically capture the echo loops for you, which is pretty neat. And if you're wondering if these things could be combined, that has been done too. This is a neat study that used 8 untrained nurses and did transthoracic echoes on 240 patients, pitting a trained sonographer against a nurse using this type of image assistance. They found that it worked exceptionally well. And so the untrained nurses were able to get diagnostic quality images, ejection fraction size, pericardial effusion on 99% of patients, and pretty good performance for RV size as well. Let's turn our attention next to the limitations of machine learning. And probably one of the biggest is that AI still doesn't understand the meaning of things. So you see this bald gentleman here. You might think, well, this is a bareheaded man who needs a hat. And if you take that phrase and put it into Google Translate, you'll see that not only does this gentleman need a hat, but what you get back from a translated phrase is the bareheaded man needed a hat. Sounds the same, is not the same. And it may be that there is a bareheaded man out there, and this bareheaded man may also need a hat. But I think this demonstrates well that the AI doesn't really understand what those things actually mean. These systems are also hackable, and minor disruptions can throw them off. So this looks to you like a stop sign, as it does to an AI algorithm that is meant to identify these with good accuracy. And if we add some stickers to you and me, this is still a stop sign. But to the AI algorithm, in which the authors evaluated, they found that in a lab setting, this fooled the machine 100% of the time and 85% in a real life test. Models are also vulnerable to changing assumptions. And so here's a model that we created at Vanderbilt using the Bayesian susceptible infected recovered model for predicting COVID inpatient census 6 weeks out using state data. And this worked very well until we started getting transfer requests from Alabama. And then the model output was wrong because the assumptions that had gone into it no longer held. So where do we go from here? Hopefully, I've demonstrated that we have faster, cheaper computers that have enabled cool technology, that we have good algorithms for image interpretation, but we still have a lot of work to do in terms of determining clinical impact when operationalized, and also understand how we can use these models to improve health as well as healthcare delivery. Thank you very much for listening.
All right, I think we've slowed down in terms of the people adding. Thank each of you for the participation in the panel. I thought it was excellent. I'm biased, of course, but that was a great talk, each of those, and really stemmed the whole breadth of I think where we're at in terms of machine learning. Again, all the participants, please post any questions in the chat, and I'll serve as your moderator. My name is Mike Burns from the University of Michigan. I'll start with a question for the panel. Say, for instance, you're at an institution that doesn't have, oh, actually we have one. So here's a question. What is the requisite sample size to train a machine learning algorithm? Is there an algorithm to estimate training and validity samples before the study?
I can certainly take on the first one of those. The answer is there is no requisite sample size kind of out of the box. Machine learning studies have been published on data sets with as few as 20 patients, but because the model starts from a position of no knowledge, the more samples you have to train that model and the more of the two classes you're trying to predict. So the more of the positive and the negative outcome imbalance that you have, the more the better performance you're going to get from that model. So size is important, but the bigger the better is really as far as I can answer. Does anyone else have anything to elaborate on that?
I can add a little bit to that, and I think Hannah answered that very well. We don't have any established algorithms as we do in statistics for estimating the training or validation sample size, because we are dealing with highly nonlinear model, and especially when we are dealing with something like the large language models that we see these days with billions of parameters, it's very difficult. There have been recently some studies to estimate an upper bound, but most of the time those upper bounds are very loose upper bounds that in practice do not help us that much. So I think from theoretical point of view, still deep learning especially, it's maybe lagging a little bit behind. We have been focused a lot on the applied side, but the theory, it could use a little bit more help in that area. But I think the short answer is that there are no established ways to estimate the number of samples. And it's a very difficult problem, and I think it's going to stay unanswered probably for a long time.
And I would just add that for sort of a simpler model like a logistic regression that isn't necessarily after all those nonlinear characteristics, if you look at sort of recommendations out there, folks will recommend having 10 to 50 events per parameter that you're going to add, an event meaning something that has the outcome of interest. And so it's not just a number of cases that you're putting into a machine learning algorithm, it's how many have the outcome of interest, which is particularly important when you're looking at things that have relatively rare outcomes.
Great, I'll pose a question. So say you're at an institution that doesn't have any ML capabilities thus far. What does it take to really get this up and running in your department? What sort of collaborations do you need? What sort of resources would you need?
I think probably the hardest part is getting a really good data set together. And I think those of us who've tried to put these models together can appreciate that. And so I think, oftentimes it's possible to collaborate in terms of the mechanics of and technical knowledge of how to put a model together, either within your institution or beyond the boundaries of that. But oftentimes the hardest piece can really getting access to data and then the cleaning process and to get it into a format that is workable. So that's certainly a first step to start with.
Anyone else?
I definitely agree with that. And also this was, I think, part of Jonathan's talk, that it's not just developing the model, that's the first step. But then once you've got that going, you also have to have like a plan of what to do with it. You have to recognize how this model is going to impact practice.
and then introduce it. And that takes a whole different skill set and engagement of your clinical colleagues.
Mm-hmm. I think in the future, with the development of ML ops tools, hopefully this will become a little bit easier in terms of managing how the models can be monitored as we are adding more and more data, as there are new guidelines added. So the development of new tools can help in this area to some extent, but still I agree that obtaining the data, that's probably the most difficult part.
So along those lines, once you have these models in place, what sort of maintenance is required?
One of the things that I can point to is the shift in dataset distribution. And that might be because of a couple of different things. It might be because maybe the patient population is changing, and maybe because the guidelines that were used when we developed the model are very different from the guidelines that are being used 2 years down the road. And therefore, the model might not be as effective as it has been in the past. So the drift in the dataset distribution, that's a problem that I think we see most often. And that is something that needs to be monitored because the performance of the models might be impacted over time. So we might need to update the models. It's not a one-time job.
And I would just add on top of that, probably depends to some degree as to what's actually in the model and sort of what you'd expect for baseline changes. We're in the process of evaluating a model that we've built for predicting intraoperative blood transfusion, which uses the identifier of the surgeon as one of the data elements. And so obviously, if we do end up implementing that, that's something that we'll need to update frequently as surgeons arrive and leave as practice changes. Whereas if we had used other characteristics, it might be something that would need less maintenance over time.
John, you mentioned that you were able to implement some machine learning models directly through Epic. Do you have you had success integrating Epic models you've created outside of Epic back into that software using maybe their cognitive cloud?
So we've done that in all sorts of different ways, and so we've done some implementations of Epic's out-of-the-box models, both with and without the cloud component. We've had some models that we developed prior to implementation of Epic, where we wanted to, or didn't really have a need to re-implement it. And so we were able to interface in the model results. And so that was for prediction of postoperative acute care needs and readmission risk. It certainly worked from a technical standpoint. A downside of doing that is you don't get the nice, pretty little hover bubble that explains sort of what's giving you that model prediction. So you lose a lot in terms of not getting the explainability that the native models offer. And you can also, of course, create your own patient acuity scores in line in Epic as well. We've done that too. And you can build in your own explainability as part of that. And so I think all that's possible. It's just a matter of local infrastructure and also potentially what your institution has licensed from a technical capability standpoint.
So another question in the queue, what is the cost for development and implementation of standard models? I know we mentioned earlier about what it takes to get these up and running, but and maybe Adam can weigh in a little more of the specific question. You mean physical dollars and what it's going to cost to get these things?
So thanks. I'm sparing you from seeing me on my Sunday afternoon Zoom, but you know, especially at Vanderbilt, do they have a way of thinking about or accounting for the kinds of models that Jonathan was just talking about? Do they know in advance what the new costs are going to be and what existing costs they may have to absorb when they set up one of these models?
I think that's an excellent question. I think the reality is there are a lot of fixed costs associated with the infrastructure that are sort of hard to break down on a per model basis. So out of the box, with at least the Epic licensing that we have, you get 10 models that you can implement and you can pay on top of that. And so it's hard to sort of say exactly how much one model would cost. From an implementation standpoint, it really is just sort of people's time and how much they have allocated to those sorts of efforts. And so you ultimately need a number of different skill sets to implement these things and keep them up and running. But we've not really tried to translate that to a direct cost internally, but certainly we do make estimates for budgeting purposes for grant work, say. And that's just on a fractional FTE basis on our best estimate. But we don't really have a great cost per model just because there are a lot of variables and a lot of the expenses are fixed.
Jonathan, that's a really helpful answer, and thank you. When you begin a model like the one you just described, do you have an idea and say, okay, it's going to take 20% of John's time and 30% of Liz's time for the next 6 months? Do you approach the model that way, or do you come up with the idea first and see where it's going, or prioritize ideas above costs?
That's a great question. So we, to be honest, we would sort of put people and names to paper for the purpose of putting grants together. When it comes down to actually building models, it depends upon who can get interested in a project. And so the one that I mentioned around intraoperative transfusion, so data set was pretty easy to put together. I did it myself, just took a couple hours. Granted, I know our models pretty well from the data model underneath it. And then I got one of my colleagues who was at that time in his residency, interested in building that out. And so he took a free online course. I gave him the data set. We had an IRB he put together, and then sort of on his own time plus residency research block, was able to both learn some of the underlying tools as well as build a proof of concept of the model. And so I guess that would be sort of 3 months of resident time, depending upon how you count it, plus a few hours of my time. And now as we're looking to implement it, that's a different question. And now we're looking at what would it take to put it in our cloud architecture. Probably we won't get like a cost for that. It'll just be something that we do as a proof of concept, but we don't build out. But if we were to write a grant about it, certainly we would translate that to FTE estimates on a per skill set basis.
Thanks very much. Really helpful.
So maybe 1 or 2 more questions. Kendrick asks, with possibility of leaking information from the train set, depending on how you explore the weights, do you have any thoughts on how interacting and sharing models will keep identifiable patient data private?
Mm-hmm. So one thing that we have been exploring at University of Florida is using federated learning models. And basically that allows you to keep your data at your own institution, but instead sending the weights of the models or gradients to a central server. So you still keep the model. Now, as you say, still there might be some issues when you're even sharing those weights or gradients. And one of the methods that we have been pursuing is using certain cryptographic methods in order to make sure that the data as well as the weights and any information that gets communicated between the parties, it stays private. And there are lots of different types of cryptographic methods. For example, the multi-party encryption methods, those allow you to encrypt the data and also just when everybody has sent the information, then one party can merge the information together. So I would say there are some workarounds for this problem, but still some research is needed. It's not a solved problem.
Okay, I think we might have time for one more question. This has to do with the maintenance as well. But is maintenance at our institutions typically handled by your team, or is there a central institution-wide team? I'll comment and say it's usually our team from Michigan, but
we have a bit of both. So folks who do all model maintenance, then we have a knowledge management team that will come around once a year and poke you and say, does this need to be updated? So
I agree. Yeah, it is both of those, our team as well as the integrated data repository team that we usually set some costs for them in grants.
Okay, I think that's about all our time. So thank you again to the speakers. Thank you for everyone for coming. And you can reach out to any one of us and ask some more questions. But again, thank you for the excellent talk.
thanks.